Hey everybody, Brandon Lewis here, aka Techie Lou of DevHeads, and we're back with my friend Amesh Lakonde, and we're really excited today to be sharing with you some guidance on how to implement CAN firmware with STM32. Obviously, that's an ARM Cortex-M device, and Amesh is going to be walking us through some of the basics, and then also, as he always does, give us a little bit of a hands-on demo at the end. You're in for a treat. Make sure that you make use of the chat box because I'll be there. I'll be sorting questions and getting things all organized for a Q&A at the end of the hour where you'll have a chance to talk to Amesh, ask him any of your questions about how to implement CAN or other things related to embedded and IoT design. Before we get going, though, we have to do the obligatory housekeeping around the platform, just so that in case you encounter any problems during the stream today, you are able to get back on track. So if you're in the webinar platform, you may not be, you may be at LinkedIn, you may be in Discord, you may be on YouTube or Facebook or elsewhere. Right now, if you're inside of the Livestorm webinar platform, I'm going to direct your attention to the bottom of the screen where there's a navigation. It's got a help button that has a little bit of a wizard that'll walk you through how to get yourself back if you lose connectivity. There's also some various buttons down there that will allow you to interact with the webinar. Mostly the questions tab, though, is what's of importance. I really encourage you to use that in the chat like I just mentioned. If you do encounter problems, a couple of best practices are go to speedtest.net. If you're pulling less than 5 megabits per second down, you're probably going to encounter issues with the stream. So see if you can change your network. Also, try to close any applications that may be consuming bandwidth or system resources. That can help. And then no matter where you are, no matter what platform, if you mention me, so I'm either at Brandon Lewis or at Techie Lou, if you tried everything else and you just can't figure it out, ping me and I'll do my best to direct or private message you and see if we can't get you back up and running. Anyway, you didn't come here to hear about how to use online platforms. You came here to hear Amesh talk about CAN. So with that, I'm going to pass it off to Amesh. Amesh, take it away.
Hi, everyone. I hope you're excited to explore the canvas. I'm going to start off with the demonstration. So before slides, let's go and see the demonstration. I hope you see on my screen, there's this software that's open. It's called Kangaroo, right? So I'm just holding up this hardware. So I hope you can see the hardware. And look at this. If I go to measurement, and if I start capturing the frame, because I have connected the real hardware, so you see the data starts coming up. So the demo that I want to show you is to control this LED by sending the CAN frame from this software. So if I go to transmit section here, you can see the ID is 322. The data length is 1 byte. So we are basically sending this number 0. And when the 0 will be received onto the CAN node, and CAN node is basically, in this case, this STM32 microcontroller. So let me press the send button, and you can see the LED light up because the CAN frame is received, so we can able to control the hardware. So if I press the send button, okay, you can see the LED lights off, right? And there's this awesome feature here in the software called send repeat. So if I click on this, it will repeatedly sending the CAN frame. And now you can see it's just toggling the LED. So this is what we basically would be end up doing by end of this session. All right. So I hope this is exciting enough for you to learn how we can transmit and receive the data over CAN bus. So let me just disconnect the hardware and measurement stop. And let's go back to the presentation. I hope this demo basically put things in perspective, like what is the end goal for the session. So let me start off. I hope you're excited to learn about the CAN bus. And we are basically implementing the BX CAN peripheral on STM32 microcontroller. So the agenda today is we're going to start off with an overview, like why and how the CAN is significant. Then we'll look at the features of the CAN bus. Then we'll dive into the CAN transceiver, the transceiver chip that we will be using today is MCP2551. That's from the microchip technology. And we'll dive into why we need transceiver chip in the first place, and then how to use it. And then we'll get into the data frame format, because in the CAN protocol, we have the standard CAN frame, and then we have an extended CAN frame. Then we will analyze the CAN frame using this adapter called USB to CAN FD adapter. This is from the VX Studio. It's a low-cost hardware. It does serve the purpose, and I will show you step by step how to configure and use it to capture your CAN frames. And then I will show you live demo where we will program the BX CAN peripheral of STM32 microcontroller. And then we will basically transmit and receive the data, I mean, basically the CAN frames. And then we'll summarize all the things that we have seen so far today. And towards the end of the session, if the time permits, then we'll take the question. So let's just talk about the CAN bus. So CAN bus is a multi-master. So far, we have seen most of the protocols in our engineering hour sessions, and most of this protocol works in master-slave communication. That means it depends on the master if it requests. But here in the CAN bus, because it's a multi-master, every device, every CAN node can able to send the data, okay, data frame. So it's unique here because there's no typical master and slave communication here. Basically, every CAN node is a master. Then in the CAN, we have a configuration flexibility. We can configure the baud rate and other settings. We'll get into that in a moment. We can also make the messages to be prioritized. So let's say if you have a certain message in your embedded system or solution, which is really very important, just like in the vehicle, you have an airbag, which is very, very important, and it has to fire it up. So it has to have an highest priority. So you can set the priorities so that whatever data is important, you can put at the high priority. Then we have the ability to guarantee the latency time in the CAN bus. So basically, it allows us to achieve the predictable timings when you send and receive the data using CAN bus. Then using CAN, it gives us the ability so that the system-wide data consistency can be achieved. So when you have a number of CAN node across whom you are sending and receiving data, you can basically achieve the consistency between data transmission and receiving. Then in a CAN protocol, we have a built-in error detection mechanism. And this is achieved by using CRC mechanism, cyclic redundancy check. And also we have an acknowledge ECK and NACK bit. If you can use it efficiently while coding, then you can literally be able to make sure that there would not be any error in between the transmission of the data. And it basically ensure the data transmission happens properly. And the multi-node communication in a CAN bus happens over twisted pair. And twisted pair means just the two wires, right? CAN high and CAN low. And this is very significant in a CAN bus because the invention of the CAN bus, the development of CAN bus itself has to do with this. Because in the older time, the vehicle had very complex wiring. So what happens is by using just a single twisted pair to transmit and receive the data in the CAN bus, you basically reduce the wiring and the harness. So it will be very lean and clean communication between the devices. Also, it reduced the cost, and also, as we talked before, it's very predictable communication, right? You can predict the data transmission with the timings. We'll get into that. I will show you live demo. So this all feature basically makes the CAN become a contender. And you have seen a lot more use of the CAN bus in automotive as well as industrial automation, and many use cases in even in the healthcare products. So let's just look at the CAN bus network. So I have here a picture where we have several ECUs placed, and this ECU are communicating with each other over CAN bus. So there's only a single twisted pair like CAN high and CAN low, and all this ECU can exchange the data between each other over the CAN bus. Now, the reason I put this slide is because I want to make one point very clear. Very often you might hear me using this word called CAN node. So CAN node is basically uh, CAN node will represent ECU into the automotive industry. So let's say if somebody associated with an automotive industry, they would refer CAN node as an ECU, but ultimately the CAN node and ECU is the same thing, right? Let's look at this next slide. So let's look at the CAN topology. So here I have shown a single CAN node. Let's put two more CAN nodes. So we have three CAN nodes here. And all these three CAN node communicate with each other over just the two wires, which is CAN high and CAN low, which is again a part of that single pair twisted wire. So just using two wires, you can able to communicate multiple CAN node. Just to make sure that we have to make sure that we add this terminating resistor just to make sure the data transmission happens properly. So it's basically reduce the transient responses or transient signals onto the data line like CAN high and CAN low. So this is how the communication happens. So by now you have realized that ECU is the same as the CAN node, right? I prefer to call it as a CAN node personally because I use CAN protocol for industrial automation, not much as of now used for the automotive. But it's the same thing, by the way. Now let's look at what is a CAN node. What exactly the CAN node is. So look at this picture here. We have a microcontroller application, and this microcontroller application is communicating with the CAN controller. And there is another piece and block which is called CAN transceiver. Now, this means that the CAN node consists of three uh, components. One is the microcontroller application, CAN controller, and CAN transceiver. Now, in the modern microcontrollers, let's say if we take an example of STM32 microcontroller, then the CAN controller comes built into the microcontroller. That's why this microcontroller and CAN controller comes together, right? At least in this picture here. But CAN transceiver, when you wish to do CAN communication, you must have to have this CAN transceiver. This is an external module that we have to connect. So the way this CAN transceiver connects to the CAN controller, because CAN controller is a part of the microcontroller, the microcontroller itself has the pin called CAN RX and CAN TX. So using this CAN TX and CAN RX pins, we can able to connect the CAN transceiver with a CAN controller. Now, you might wonder and ask this question, what is a role of CAN controller and what's the role of a CAN transceiver? So CAN transceiver, let's look at this. So CAN transceiver basically takes the real physical signals. So real physical signals is coming from the CAN bus. That's a CAN high and CAN low, which is basically at very physical layer, right, of the communication. So the CAN transceiver takes the real physical signals from CAN high and CAN low, process it, and convert it into the digital logic level 0 and 1, logic high and logic low, and then push it into the CAN controller. Now, the CAN controller basically helps to set the baud rate, and then the CAN understand and interpret the data or maybe the signal that is sent by CAN transceiver. Okay, and that data, once that data or the signal CAN high and CAN low will be interpreted by a CAN controller, it will be used by a microcontroller firmware to process the data and build an application on the top of it. I hope this is very, very clear by now, how the CAN transceiver helps to communicate to the external real physical world where the actual data is transmitting. So this is how the CAN node is made. Now let's just look at more detail about CAN transceiver. And the CAN transceiver module that I'm using, that's use the chip called MCP2551. That's from the microchip technology. And you can see there are pins here, CAN TX and CAN RX, that will be used to connect to the microcontroller. And CAN high and CAN low is to communicate with the CAN bus. So the role of a CAN transceiver, as we spoke before, it handles the bus connection. It provides the high noise immunity, because normally in the microcontroller is not capable to handle a signal which has a noise. And you probably agree with me that in the factory environment or into the automotive, the noise that is generated around your vehicle or maybe around your electronics is really high, and there will be a risk of losing data in between or the collision between the data transmission. So it's always makes a sense to use the high noise, I mean, to have a mechanism which can allow us to communicate or exchange the data even in the noisy environment. And that's why we need the CAN transceiver. So this transceiver gives us the CAN high and CAN low pins through which we connect to the um, bus, CAN bus. Now you have to understand there are two types of CAN bus. okay, like CAN transceivers. So one is the high-speed CAN transceiver, and the other one is a low-speed CAN transceiver. Now, high-speed CAN transceiver can achieve 1 megabits per second. So when you want to achieve the data transmission over CAN bus very, very fast, then you can use the high-speed CAN transceiver. And by the way, this one, MCP2551, is a high-speed CAN transceiver. The other one is a low speed CAN transceiver, which allow us to communicate up to 128 kilobits per second. So now you might get the question like, why would somebody use the low speed for communication using CAN bus? So sometimes you want to drive the data much far, maybe a longer distances. And whenever you want to send data little far, then you better use low speed CAN transceiver. Okay, because then you reduce the chances that the data would be lost in the communication, or maybe the collision or some other error that can be minimized. And whenever you want to transmit the data over shorter distances, then it's recommended to use the high speed data communication, which is 1 megabit per second. Okay, so I hope this makes a sense. Like in the transceiver you have a high speed and you have a low speed. Now, let's talk about the setup, the test setup that I have done here at my end, the connection, how we made it. So on one side, we have the microcontroller STM32 nuclear board, STM32F303, and it is connected with the CAN transceiver. So you can see clearly CTX, CAN TX, and CAN RX is connected to the microcontroller here. And then we have one LED connected to PB0 pin. That's the LED that I wanted to control. So when you put the microcontroller, and this STM32 modern microcontroller comes with a built-in CAN controller. So this STM32 with CAN transceiver form the CAN node, right? And on the other side, we have a computer, the host PC, on which we have a software that is installed called Kangaroo. This is coming from the VX Studio, the hardware that I'm using. So this software will be used to analyze the CAN frame. Okay, so now you might ask the question like how the CAN communicates, like because this transceiver communicates over CAN high and CAN low, just the two wires. And on the other side, we have the host PC. So we put in between USB to CAN FT adapter. So this adapter basically takes the CAN data over CAN high and CAN low and then process over the USB and then get it to the host PC. And I will show you live demo how this communication actually works in the real world. But this is what the setup is all about. Now, when we have to write the firmware for the STM32, especially the BX-CAN peripheral, then we have to understand the block diagram, because that's the logic that the ST has implemented to achieve the CAN communication or to use the CAN protocol with the STM32 microcontroller. And you can see, as this block is the CAN block, we have one acceptance filter, then we have a receive 540, receive 541, and then there is a TX mailboxes. There are only three components that you have to really understand when you are using the BX-CAN peripheral in STM32 microcontroller. So one is a TX mailbox, TX, the transmit mailbox. So this transmit mailbox is the place where you keep your messages that you want to transmit from your CAN bus. Okay. Then the FIFO register, FIFO0 and FIFO1. There are two FIFOs and there are three transmit mailboxes, 0, 1, 2, 0, 1, 2. There are three transmit mailbox boxes. That means you can store three data that you can transmit. To receive the data over CAN bus, you can make use of receive 540 and receive 541. So there are two receive 54 in which you can store your data. And this 54 is connected to the acceptance filter. Now, you might wonder what is acceptance filter and what its role is, because we are clear the transmit mailbox is to store the data that you want to transmit. The receive FIFO is to store the data that you want to receive, right? So whenever the data received, it will be into the receive FIFO. Now, the acceptance filter is basically connected to this FIFO registers, and this acceptance filter has a 28 filter banks. You can see filter 0 to 13 it's shown, but it's like a 0 to 27, so it's like a 28 filter banks. And don't bother about this master filter and slave filter. This is a little bit misleading, but it doesn't have any logical meaning here. The reason why in the STS document they say master filter and slave filter is because in case in your microcontroller you have two CAN peripherals like CAN1 and CAN2. So in that case, in the STs CAN design, they use CAN1 as a master and CAN2 as a slave. But remember one thing, in the real world CAN communication, there is no concept called master and slave. There's nothing master and nothing slave, right? Everything is just a CAN node, and everyone can be a master. But just my point is that in the acceptance filter, here we have a filter banks from 0 to up to 27. So there are 28 filter